So designation of tool geometry, so also known as tool signature. So that means, so if you go for buying any cutting tool, so we are discussing about single point cutting tool. So if you go to buy a single point cutting tool, its specification so will be given like this. So for the particular depending on the type of system they are following, okay, so in the specification you can see 10 degree, then minus 8 degree, 7 degree, 6 degree, 15 degree, 30 degree, and 1/8 inch. Okay, in order to understand, so what do you mean by this 10 degree, 8 degree, 7 degree, 6 degree, all this? So you must be aware of the different systems. Okay, so you used for denoting these details or denoting the geometry or representing the tool geometry. So the geometry of a single point tool is designated or specified by a series of values. So like this series of values of the salient angles. So salient angles means rake angle, clearance angle, and cutting angles. Those are the salient angles. Rake. Okay, so rake, clearance, and cutting angles. And nose radius arranged in a definite sequence as follows. It is ASA system, so that is American Standards Association system. The another name for this system is machine reference system. Okay, so gamma y means, so it is the back rake angle. Okay, gamma x is the side rake angle. Okay, so this is the back clearance angle, this is the end clearance angle, so this is the end cutting edge angle, so this is the principal cutting edge angle, and this is the so radius of nose radius. Okay, so in this case, so 10 degree is the back rake angle. Okay, minus 8 degree is the side rake angle. Okay, so this is the back clearance angle, and this is the end clearance angle, this is the end cutting edge angle, and this is the principal cutting edge angle, and 1/8 inches is the nose radius. Okay, like that in ORS also, inclination angle, then orthogonal rake angle, orthogonal clearance angle, so then auxiliary orthogonal angle. Okay, then end cutting edge angle, then principal cutting edge angle, then nose radius. In case of NRS also, inclination angle, then normal rake angle, normal clearance angle, then auxiliary clearance angle, okay, then so end cutting edge angle, principal cutting edge angle, and radius, nose radius. Okay, so in this figure you can see this is the tool geometry for this tool. Okay, so this is the front view, this is the top view, and this is the side view. So here they followed third angle projection. That's why they drawn top view above. So this is third angle projection. Usually we follow first angle projection where top view will come below and front view will be always above. That is first angle projection. But these are the orthogonal views while we are following the third angle projection. The top view will be above. Okay. So here you can see 10 degree, 20 degree, 7 degree, 6 degree, 8 degree, 15 and 0.8 mm. Okay, so this is called known as tool signature. So that means series of values representing tool angles and nose radius. Okay, tool angles again rake angle, clearance angle, cutting angles. So these two are the rake angles, and these two are the clearance angles, also known as relief angle, and these two are the cutting angles. Okay. And last one is the nose radius. And next, mechanism of chip formation. We move on to the next topic. So that is chip formation. We know during machining, material will be removed in the form of chips. Okay, how these chips are formed? Okay, so and different considerations related to chips. So all those things we discuss. Okay. Almost all the machining parameters that is tool geometry, levels of process parameters, and the machining environment play significant role on the pattern of chips. So that means tool geometry will decide how chips will, or the formation of chips is decided by tool geometry. Tool geometry means again angles, cutting edges, okay, so and nose radius, that is the tool geometry. Levels of process parameters, okay, there are three major process parameters. So which are the three major process parameters? Nenpidya. So if you know, you can answer. Which are the three major process parameters? Okay, cutting velocity, depth of cut,
Cutting
speed.
speed, cutting velocity.
Okay, so there are three major process parameters: cutting velocity or cutting speed, then feed or feed rate, and depth of cut. Okay, depth of cut is also known as cross feed. Okay, feed or feed rate is also known as longitudinal feed. Those three are the process parameters: cutting velocity or cutting speed, depth of cut, feed. Okay, so levels of process parameters means again the value that you are going to specify, that is the levels of process parameters. Then machining environment. So what do you mean by this machining environment? So it is related to application of cutting fluid, whether machining will be performed with cutting fluid or whether it is performed without cutting fluid. If it is performed with the application of cutting fluid, then it is called as machining under wet conditions. So wet means you are applying the cutting fluid. Then there is another possibility, that is machining with dry condition. That means you are not applying the cutting fluid. Okay. All those will be having an influence on pattern of chips. Okay. We are going to discuss about this in detail. Based on shape, size, and color, the machining chips are categorized as favorable chips or unfavorable chips, indicating good machinability or poor machinability. So we discussed about machinability. What do I mean by machinability? Really, machinability andrena? What do you mean by machinability? Really, ಯಾರಾದರೂ ಹೇಳ್ಬೋದು. Okay, machinability is the measure of ease of machining, how easily you can perform machining operation. So that means how easily you can remove material, extra material or unwanted material, how easily you can remove it. So that is denoted by machinability. Okay, so always we expect good machinability. Okay, so again that is also having influence on the chips. Favorable chips can be obtained through proper selection of machining condition. So that means proper selection of machining condition. Machining condition includes proper selection of tool geometry, then proper selection of process parameters, that is cutting speed, depth of cut and feed, proper selection of cutting fluid. Okay, so that means the quantity of cutting fluid that you are going to apply. So all those things decide machining condition. So it depends on tool geometry, levels of process parameters, and machining environment. All this will decide the machining condition. Okay, the mode of chip formation and form of the chips are important indexes of machining. Okay, next, the features and characteristics of machining chips widely vary depending upon work material, brittle, ductile. So can you give some examples for brittle material? Brittle, brittle material?
Cast
Give
iron.
few examples. Cast iron. Then
Copper.
ductile.
Glass.
Ductile. Copper is the ductile material. Then
Copper.
so
Gold.
copper, aluminium, mild steel.
Gold.
Okay, so gold. Okay, all these are ductile materials. Cast iron is the brittle material. Okay, so you can consider another example. Okay, so if you consider human bone, ಸೊ ನಮ್ದು ಮೂಳೆ ಇದೆಯಲ್ಲ, ಮೂಳೆ ಬ್ರಿಟಲ್ ಡಕ್ಟೈಲ? ಹ್ಯೂಮನ್ ಬೋನ್
ಡಕ್ಟೈಲ್.
ನಮ್ದು ಮೂಳೆ ಇದೆಯಲ್ಲ ಡಕ್ಟೈಲ ಬ್ರಿಟಲ್?
ಸರ್ ಡಕ್ಟೈಲ್.
So you are telling that human bone is ductile. So but ನೀವು ಎಲ್ಲಾರ ಬಿದ್ರೆ ಯಾಕೆ ಫ್ರಾಕ್ಚರ್ ಆಗುತ್ತೆ ಮತ್ತೆ? ಇಫ್ ಇಟ್ ಇಸ್ ಡಕ್ಟೈಲ್, ವೈ? So there will be fracture. So human bone is brittle. ಓಕೆ, ಸೊ ಡಕ್ಟೈಲ್ ಆಗಿದ್ರೆ ನೀವು ಬಿದ್ದಾಗ ಬೋನ್ ಡಿಫಾರ್ಮ್ ಆಗಿ ಬೇರೆ ಶೇಪ್ ತಗೊಳ್ತಾ ಇತ್ತು, ಬಟ್ ಫ್ರಾಕ್ಚರ್ ಆಗ್ತಾ ಇರಲಿಲ್ಲ. ಓಕೆ, ಬಿಕಾಸ್ ಹ್ಯೂಮನ್ ಬೋನ್ ಇಸ್ ಬ್ರಿಟಲ್, ಸೊ ನೀವು ಬಿದ್ರೆ ಕೈ ಮೂಳೆ ಬಿಡ್ಕೊಂಡು ಫ್ರಾಕ್ಚರ್ ಆಗುತ್ತೆ. ಓಕೆ, ಸೊ ದಟ್ ಈಸ್ ಬೋನ್ ಇಸ್ ದಿ ಗುಡ್ ಎಕ್ಸಾಂಪಲ್ ಫಾರ್ ಬ್ರಿಟಲ್ ಮೆಟೀರಿಯಲ್. ಓಕೆ, so in case of brittle materials, so that doesn't have much tensile strength. Because of that, if you try to deform it, so there will be fracture. That is about the brittle materials. Whereas in case of ductile material, so they will be having some amount of tensile strength. Because of that, when you apply stresses, so deformation takes place. That means they will take a required shape or desired shape. Okay, so that is about brittle and ductile. So example for brittle, cast iron. Example for ductile, okay, mild steel, copper, aluminium. Next type of machining, continuous interrupted. Okay, if you are able to perform machining continuously, if you are removing material from the work part, that is the continuous machining. Interrupted means with breaks. Then material and geometry of the cutting tool. So we have discussed about geometry of cutting tool. So that means nose radius and angles, different angles, rate, clearance and cutting angles. That is the geometry of cutting tool. And material of the cutting tool. So in next module we discuss about different materials used for cutting tools and their properties and merits and demerits. Okay, so that we will discuss later. Levels of the cutting process parameters. So that is level of cutting velocity, feed, and also to some extent depth of cut, that is the cross feed. Okay, machining condition, dry or wet. Again, if you don't apply cutting fluid, that is the dry condition. If you apply cutting fluid, that is wet condition. Type and method of application of cutting fluid. Again, so the quantity of cutting fluid that you are going to apply to the machining zone, based on that, so you are having different types and methods. Okay, so that affects cutting temperature, friction and tool wear. So these are the functions of cutting fluid. If you apply cutting fluid, with the help of that you can reduce the temperature. So since cutting fluid is going to carry away the heat in the machining zone, so you are able to reduce the cutting temperature. Then it is possible to avoid friction, or it is possible to reduce friction by applying the cutting fluid. Okay, because of that again it is possible to reduce tool wear. This will all these things we will discuss in next module. Okay. Next, basic mechanisms that accomplish chip formation or yielding for ductile materials, fracturing for brittle materials. So that means fracture with, if you try to apply load or force on the brittle material, then fracturing will occur. In case of ductile materials, deformation takes place. So that means yielding means deformation. Okay, so yielding takes place at the end of elasticity and at the beginning of the plastic deformation, yielding will occur. Okay.